how's everybody doing? Good? Everybody remember we have an exam on Wednesday? Does anybody else have an iPhone that like overheats now that it has iOS 18? Just curious. Yes? Yeah. Ever since I updated mine, it's just like going at something 100% all the time in my pocket, and it is miserable. So just thought I'd survey. All right. And things more related to data structures. This is this week. So we have, challenge 3 will be here soon. So we're here, we'll do our review today for exam 2. We'll do exam 2 on Wednesday. We will not have class on Friday because if you think about it, right, there are Tuesday, Thursday sections of this class, and they spend a week on an exam. They have a review day and they have an exam day. We should just spend a week on an exam. Well, we get ours done in 2 days instead of 3. So we'll take Friday off. Take that time to look at your challenge. It'll be related to binary search trees. Okay, so exam 2, review. So there's a summary sheet, just like last time, on Canvas that has kind of just a high level of everything you need to know for this exam. There is an SI practice test on Canvas as well. It's got a few things, and we'll look at it, a few things that really don't apply to us that you don't really need to know how to do. And it's got, mostly it's stuff that overlaps between all the sections. We'll do practice questions in this presentation, and I'll answer any questions you have about anything specific. So to start off with, on the exam, you will get this information. This will be printed on the exam for you, so don't spend any time trying to memorize this or worrying about that. So this is just telling you how to calculate the height of a node and how to calculate the balance factor of a node. And then this is, if you remember when we do those rotations in AVL trees, this is kind of that identity where you can fill in whichever nodes you have to these patterns and then transform them in that way. So don't worry about memorizing that. There's really no reason to. So the structure of the exam, we'll have more questions this time, but a lot of them are short questions. So there will be 7 questions on tree basics, and these are very basic. Then we'll do 10 on binary search trees, so that's kind of the bulk of the exam. About half of them are short, half of them, you have to do a little bit of tracing something through. We'll have 4 on AVL trees, 5 on heaps, and then we'll have 5 bonus questions on this exam. So there is an opportunity to earn quite a few extra points on the bonus section on this exam. So if you didn't do so well on the first exam and you want to make up for that, or if you want to store up in anticipation of the third exam, this is a good chance to do that if you have, time to study a little bit extra. I'll tell you what some of those questions are. So on the tree basics, of 7 questions in this area, and they will be essentially, we'll have a tree and you'll identify certain nodes in the tree, so it's kind of multiple choice or matching in that sense. And then I think there's 1 or 2 that are just straight up multiple choice. So what those questions look like are things like this. So you'll just be given a tree, and again, it's not a binary search tree or a binary tree even, it's just a general tree. And we'll have questions about, what is the root node, what is the height of a certain node, the degree of a node, children, parents, those basic questions about relationships within a tree. So all of this is covered in our first trees lecture, and it's all on the summary sheet as well.
So the degree node, isn't that just how many cases it has?
Yes, exactly, yeah. So these should be really quick to go through on the exam. Okay, so binary search trees, which is kind of the bulk of the exam. These are the things that you need to know, kind of spelled out. The binary search tree principle, if you remember, and that's just that the left child is always less than the parent, the right child is always greater than the parent. You'll need to be able to identify something if it is a tree, a binary tree, or a binary search tree. Just remember that those 3 things are all different. You need to know how to insert and remove an element from a binary search tree, and you need to know how to do each of the traversals, the pre-order, in-order, and post-order. And so the breakdown of the questions, so there will be 3 multiple choice questions, 3 that will give you trees and ask you to select, are they a tree, binary search tree, just kind of all that apply to them. There will be 1 where you will draw the tree as you insert nodes into it, and then there will be 3 where you write out the traversals. So, sample questions could be multiple choice questions, something like the relationship between the parent and the left child, the relationship between the parent and the right child, the maximum number of children that a binary search tree can have is 2, minimum is 0. And so on the questions that are asking you to identify binary search tree, there'll be something like this. You'll get a picture of a data structure, and then you can check each of the ones that it is. So, and obviously multiple apply, because if something is a binary tree, then it's also a tree.
So what makes the difference between a binary tree and a binary search tree?
So a binary search tree has that ordered property, right? So the left child's always less than the parent, and the right child's always greater. Whereas the binary tree, it just has to have 2 children only. So in this case, you can see 14 is greater than 11, so that's not a binary search tree, but it is a binary tree.
And they all can be. So the reason why that last one out of tree is because it's all connected.
Right. Anybody know what this is? Graph, yeah. So this is a graph, and that's what we'll do next. Start connecting things multiple ways. But yeah, not a tree. Right, so basic sample question on where you have to draw out a tree. It'll just ask you to insert a series of numbers. And so you'll just start in order, so 12, and then 4, 1, and then 5 and 22. And you'll get a tree like that. Just maintaining that binary search tree. So you're just inserting, then when you do the next one, you compare to go left or right, and build that tree. And then after you do that, there will be a question to remove a node from that binary search tree. And in this case, removing 12 will yield a tree like this. There's also another valid tree that you could have if you went the other way. But
So I was thinking, couldn't it be 4 at the top?
yeah, let's see, 4.
It'd be 5.
5, yeah. Yeah, it would be 5. So if you remember, you can do, you can either go down the left side or the right side, basically, in the min or max kind of thing. So it will just be, you'll just need to do a valid response. It could be either way. They'll both be right. And I'll try to keep this simple, not too many, levels, just for the sake of you not having to spend a bunch of time doing the same thing over and over. So don't worry about it being too involved that way. For the traversal questions, so there will be a question for each of these orders, and I'll give you a tree, and you'll just output them in each order. And so if you remember pre-order, the way you do it is we always start at the node, and so in pre-order you visit that location, then you do all the left, and then you do all the right. In order is left, visit right, and then left, right, visit for post order. And if you remember, we learned a easy trick to do this, where we would draw the lines on the nodes and then start at the top left and draw that line all the way around. And then you can just go through and if you want pre-order, it's that horizontal line that's to the left. So as you start and come through those lines, you just spit it out in that order. If you want in order, it's the bottom line, and if you want post order, it's the right line there. If you want to think about it that way, that is a easy way to do it fast. If you want to, you can of course think about it as visit left, right, visit, that kind of thing. That's what that's doing. Okay. For AVL trees, there will be 3 multiple choice questions about AVL trees. some of the things you need to know about them. They're a self-balancing tree. You need to know how to compute the height of the nodes in the AVL tree, which that formula is provided to you. So just apply that. That should be pretty straightforward. Know how to compute the balance factor. You'll also have the formula for that. And you know when a balance factor requires a rotation and how to apply that. So sample questions: what type of tree is an AVL tree? It is a self-balancing tree. When do you need to balance a tree or subtree? And that's, remember, when that balance factor is either -2 or less than -2 or +2 or greater than +2. Yes?
Will we have to go over any like double rotation or anything like that?
No. So you won't have any, there will be no like left-right, right-left rotation. And there will be one, I believe, let me see if it, yeah, okay. So you'll have one multiple choice-based rotation. So you'll see it ahead of time and you'll have choices to choose from which way is right. And then there is a bonus question where you do it on your own, but it's not a double rotation, just a regular rotation. So here we go, balance factors and heights. Remember how to compute those. You have those formulas given to you, and you'll have this given to you as well, so that you can perform this rotation. And again, the question for this will be a multiple choice, so you will be able to, work backwards if you really want to, and see which one's balanced. But you should have all the information you need to do this relatively easily on the exam. All right, and the last thing is heaps. So for heaps, remember the principle of a min heap and a max heap, and be able to identify if something is a min heap or a max heap, or neither of those. Remember how to add and remove elements from min and max heap. Remember that it's stored as an array, and how you convert the node position into the array position. And then this is more for the bonus, to know the runtime related to building a heap. So for these, we'll have 3 of these questions, and you'll see a structure here, and you will label it either a min heap, a max heap, or neither. So you can see max heap maintains that property. This is greater than its children. Min heap, this is less than its children. This one does not have either property. And so the ones you get on the exam will probably have like another layer or two, not this exact simple, but quick enough for you to compute to not have to waste a lot of time on it. Okay, so there will be, in terms of inserting into the heap, these will be a multiple choice selection. You'll see the heap before, and then you'll be told, like, we're going to insert 63 here, and you'll have a set of choices of what the heap looks like afterwards. And so in this case, the right answer is like this.
Do they still like maintain
The heap property?
Yeah, I missed that class period. Yeah, I was wondering if it could like maintain the binary tree like operation, but I see like in the bottom left it doesn't. So. Right.
So the heap, the heap property is different from binary tree in that its constraint is like, okay, my children, if it's a min heap, the children have to be greater than it, both of the children. And if it's a max heap, then the children have to be less than it.
So like if it said insert, like we could see that that's a min heap. So if that number was greater than 67, then it would have went at the bottom of one of those.
So there's a kind of a way of doing this, and you can just glance back at the lecture, like the recording of it. It's real simple. So essentially, you always insert into the next available slot, and then you swap them going upwards until they're in order. It's not too bad. You'll get it if you just jump to that lecture on heaps, and you'll see the walkthrough step by step on it. It's not bad. Same thing for removing a heap or removing an element from a heap. So remember, we always remove the top element from a heap. We would never remove anything else. So there'll be a problem giving you a heap, say, and then it will ask you to choose what the heap looks like after you remove an element. For the bonus questions, this is kind of the breakdown. So it's 16 possible bonus points that you can get. So 3 of them are kind of simpler things. So two of them are related to the complexity of heaps and binary search tree operations. So just, things like what is the computational complexity of like finding an element in a binary search tree or inserting an element, and the same with like inserting into a heap. The two worth more points are, the first one is to insert into an AVL tree and balance the tree. So in that case, it won't be like multiple choice or anything. You'll be given a AVL tree and some values to insert, and then you'll just need to work out that process of inserting it and balancing it for that.
And what makes an AVL tree different from a binary search tree?
So the AVL tree keeps that balanced state, remember? Like the binary search tree could technically kind of just go off into a long line.
The AVL is like when we do the balancing factor?
Yeah, exactly, yeah. And then the second one that's worth 5 points is to remove from a heap and restore the heap property, and just kind of working all the steps out of that. So, are there questions on any of this so far?
Are these specific slides going to be posted again?
Yes, I will post these right after class. So you will have these slides. Quickly to just look at.
And you said there's this is the little test review sheet?
Yes, so this is on Canvas, and this is a review for our section in particular, so it is written with this exam in mind. And this kind of just gives you the summary of everything you need to know. So trees, binary search trees, how to, so like here's removing from the binary search tree and kind of the two different ways that could go, and just reminding you of like the different cases that occur when that happens. Here's your AVL trees, and finally heaps. And so that is on Canvas and available for you to download and study with. Also on Canvas, this is the SI exam. Have people looked at this yet? No? Okay. I didn't know if, yeah. So it is, most of these problems are problems that are relevant to our exam. So like the maximum number of children in a tree, in a binary search tree. So here's one that's not relevant. So this asks, is node A left or right heavy? We didn't talk about left or right heavy because it's kind of not important. So if you compute the balance factor of something, that tells you if it's right or left heavy, depending on the sign of the balance factor. I'm not going to ask you about that, but I bet you could guess which side of that is heavy. So that's one that will not be on our exam. What does BST stand for? I will not be asking you that. That's a little bit easy. Primary principle of the binary search tree you'll need to know. And then, yes, some examples. What determines if the AVL tree is unbalanced? The balance factor. And how to calculate that. So this practice does have you write the 4 types of rotations. We didn't do it that way, and I wouldn't want you to memorize something like that anyways, so you don't have to worry about that. Ours is just that one identity that you can apply to everything, and it's provided to you. Let's see what else we've got on here. So here's one, just building a binary search tree, which you will do. Here, these are just questions about a tree, right? Like the height, the degree, the root, the children, all that stuff we saw at the beginning. Same thing here, calculating a balance factor as well. So, and then this practice exam has the AVL trees, and it has you actually doing the rotations manually on those, so don't worry about that. It's good practice for like if you're gonna try the bonus question to do that, but the ones on our exam will be, it will just be one with the rotation and you'll be selecting, and that's mostly because we only have 50 minutes to do this exam, and you can get caught up in these things quite a bit. So it has that. Let's see what else is on here. More characteristics of a tree, and then heaps. So for heaps, this has you building the heap from an array. You won't do that unless you do that on the bonus question for us.
And so for the heap, I know like a max heap, the one at the top is the, well, yeah, I gotta go back. Like I was saying, I know the one at the top is the greatest, so like,
Mhm.
like, does it matter when you put the rest of them that's least below?
Yeah, yeah. So there is an order to it. Okay, and I think that's pretty much all on here. The rest of it is relevant. I'll post the solutions to that practice exam as well as these slides. And I'll note on the solutions like which ones aren't relevant for our class, just so you can remember that. All right, so yeah, and those are just some notes on what we won't have on our exam. Okay, so questions, areas that you want to look at in more detail today?
Me personally,
Mhm.
but the pre-order and all that stuff,
Yeah.
pre-order and stuff, and the heaps,
Yeah,
that's just me, I wasn't here that day. Well,
Okay.
outside.
yeah. You want to, let's do the pre, in order and post order stuff. Okay, so let me see if I can just do this. Actually, let's just do it with one of these. And so I'm going to just, because Keynote is not cool, just take that. Okay. Well, I really don't trust that. Okay. So, good. Let's say we have this binary search tree here, and we want to do the pre-order traversal. And so to do that, using kind of that trick that we learned. So the first thing was to draw these kind of little lines. That's fun. On each node, just like this. And you don't really have to do this once you get the hang of it, but it is kind of an easy visual indicator. Okay, so that's a little better. Okay, so once we've got that done, we'll consider this left one is the pre-order, bottom is in order, and right is post-order. Okay. And so then we always start up here, top of the root node, and then we come down to the left, and we follow this edge, we pass through these lines, come around here, we're just following the edge of the tree, back around there, around this edge, all the way up. And you're just following the exact border of the tree, however, like whatever shape it's in, doesn't really matter. And then come right back up to the top. Okay. So now to list the different orders, we're going to just, like if we want pre-order, we'll say, okay, we started up here. And then as we hit these left ones, we just spit those out, right? So in this case, 12, 4, 1, 5, 22, pre-order. If we want to do the in order, it's the bottom line. So we still start up here, but we don't get to our first one until we're all the way down here. 1, 4, 5, 12, and 22. And then if we want to do the post order, it's the one on the right. So we still start up here, we come all the way down. Again, we don't get there until we get to 1. So that's 1. Then we come back around to 5, 4, 22, and 12. So pretty good. And that gives you all 3 orders. Okay. What was the other one you wanted to look at?
Heaps.
Heaps. All right. So, quick review on heaps. here's the main properties of a min heap and a max heap. For the max heap, the parent is always bigger than the children. For the min heap.
Decide, like, why 19 on the left instead of the right?
Okay, so we will get to that. But if you just have to identify by sight, that's the property you're checking. So the heap is stored in an array. We'll not focus on that for a second. So let's do building the initial heap. So, for example, if we have this min heap that exists, and we're going to insert 63. So we always insert into this next available slot because the heap always has to fill up each level before it can go to the next. So we put 63 down here, and then we check the heap property with its parent. And so in this case, we're asking, is 63 less than its parent? And because it is, and this is a min heap, it needs to be above 77. So we do that swap. Then we go to its next parent, which is 67. And so since it's less than 67, we also need to do that swap. And then we go finally to its last parent, which is the root, and it's not less than 56. So that's where it stays. And that's the insertion. And same thing if you're doing like a max heap, just the opposite comparison. So the bigger one pushes up. Now,
And we didn't put it on the right side
because we always have to fill in wherever the next slot is on here.
so like 2 children to each of them.
Yep, 2 children to each. Yeah. And so for removing the element, it's kind of in reverse. So what we do is we always remove the top node. So in this case, 56 is what we're going to remove. And our first step, when we take 56 away, is we swap it with the last child down here, the one that's the furthest to the right on the lowest level. And that's how we start. So we'll take 56, it's gone, and then we put 77 up in its place, right? And so now we have to do the same process but going downwards with 77. And so what we need to do in this case is to choose the smaller of the 2 children and see if 77 is bigger than it. And if it is, we need to swap it because this is a min heap. So we get that, where we swap 63 in that direction. And then now we have 77 here. And we choose the smaller of the 2 children, which is 67 in this case. And we need to swap that as well. And now we're at the leaf there. And so that is as far as that will go. And so now you've maintained the heap property and removed the top node. Other questions? Any other topics? Yes?
Will we need to remember that formula that's like looking at the array and trying to find which node is the parent of it? I remember it's like floor n divided by 2 something.
I wouldn't worry about that too much, yeah. Other questions? Everybody feel good about this? Okay. On the rotations? Yeah. So the rotations on the AVL trees, let's look at some of those. So, basic example, let's say we're building our AVL tree, and as we build it, we compute the heights and balance factors for each of these, and as long as they're 0, 1, or -1, we're okay. But as soon as we get to a point, so we've inserted these according to binary search tree principle, and we've computed the balance factor for each, and at this point, the root node's balance factor is -2. So that means that we do need to do a rotation. And so to do that, we're going to just use this identity here that allows us to transform these without altering the binary search tree traversal order, which is what's the important thing to preserve. And so we can essentially overlay this pattern onto our subtree that needs to be rotated. And we can do this mapping so that this is X, this is Y, and we can rearrange these nodes where these triangles represent, full subtrees. Whatever's down there is fine. It doesn't have to be a single node. It could be nothing. It could be a ton of things. We follow that and we rotate it accordingly. And so we'll get this output from following this, which will hold the same traversal order, but is balanced when we compute those balance factors for the node. So if we keep going here, let's see, so that's balanced now. As we insert more, you can see the next time that something violates that balance factor, this time we're at this node 50. And so it is important, you start wherever the first balance factor is too high or too low, and you correct that subtree, and then you come back and continue up and calculate again to make sure you don't need to rotate again. For the exam, you won't ever need to rotate again. You'll just need to do one rotation. But in practice, if you would continue checking up the tree for this. So in this case, we're going to just split off this problem area. And I'm just copying over that section of the tree that's not really relevant right now. I'm going to apply rotation to it, and it will come out like this, and I just put it back where I found it. And then I still need to compute that balance factor for this parent node, but it is a 1 in this case, so there's no further rotations needed. We're all good there. And that's kind of the basic cases of this. So where we can, let me see if I can find one that's a little bit more complicated. The one that can be very problematic where you need to do like a double rotation is like a case like this. You kind of got this zigzag structure going on. And so you can see a single rotation just kind of pops it back the other way, which doesn't help you any. And that's when you would do something like a double rotation so that you follow this progression. We won't do that on the exam just because it takes too much time. But that is how you would do it if you ran into that case where you kind of have that structure that zigs and zags like that. But for the exam, the important thing is these basic cases of being able to detect that you need to rotate it. So just that balance factor is 2 or greater or -2 or less, and then applying this template to it to produce the rotation in one direction. Is that helpful? Are there specific parts of it?
Yeah.
Okay. And with this, I kind of find the most helpful thing is just to work through a bunch of them, especially with looking at that structure, and then you kind of get this rhythm of it and how to just balance it. But yeah, it will just be these basic rotations.
Did you say the left and right rotate formula thing was also going to be given on the test?
Yes, yeah. You will get this. This will be on the exam for you, so all you need to do is apply it. Yeah. Anything else? Okay. Well, then I think we are all good. I will see you all on Wednesday for the exam, and it will be on paper.